In this lesson, we'll show how to analyze a truss. That is, to find the forces in all the members, and we'll do so using the method of joints. A typical example of where this would apply would be to find the forces that act in all the members that support this sign. But realize that the type of truss that we'll analyze is called a simple truss. You start with a basic triangular element, which is rigid. Then you add to it two members and a joint, and continue to build upon the truss to the shape you want. Simple trusses are often used in the construction of bridges, as in this case, where they're lightweight and they can carry a large load over a long span. Here's an example of a truss that's used in the construction of an electrical transmission tower, or here, for the boom of a crane, or even here, where the roof of this building is supported by a truss made from lumber. Now, to find the forces in the members of any truss, we'll make two important assumptions. The first assumption is that all loads are applied at the joints of a truss, and so the members are all two-force members. If the joints push on the member, we have compression in the member, and if the joints pull on the member, we have tension. For example, consider the loading of this roof. It's transmitted to these purlins, which are resting at the joints of this truss. So all the loads are applied at the joints that you see here, meaning that each of the members of the truss is subjected only to two forces, one at one end and one at the other end. The second assumption we make is that we assume that the members are joined together by smooth pins, since the forces are all concurrent at each joint. For example, consider this joint. Here, all the members come together and meet at a common point. And since the force in each member is along the axis of the member, we have a system of concurrent forces that meet at this point. It's as if we have a pin here. After all, moment equilibrium is satisfied about the point. Here's another example of a truss joint. Here, all the members are connected to this plate. By the way, we call this plate a gusset plate. All the members are concurrent at this point, and consequently the force in each one of the members comes together at the point, and we can assume we have a pin right at this point of connection. Finally, here's another example of a gusset plate that's been pressed onto wood members to create a joint. And again, at that joint, we have a system of concurrent forces, which makes this an assumption of being a pin. Now, with these two assumptions in mind, we can then find the forces that act in the members of a truss. And one method to do this is called the method of joints. Now, before I discuss the method of joints, let me again repeat something that I've said earlier. A member in tension means that it's being pulled on at its endpoints. What causes that? The joints. They pull on the member and elongate it. Of course, the member pulls back on the joints. And so if we're going to look at, say, a free body diagram of a joint, and we see the member pulling, we know the member is in tension because of action, reaction. In the same way, if we have compression, the forces have to push on the ends. Using action-reaction, we see that the member then has to push back on the joints. So if we draw a free body diagram of this joint, and we see we have a member which is pushing on it, we know that that member is subjected to a compression force. All right, now with this in mind, let's discuss the method of joints. Essentially, it's based on the idea that if a truss is in equilibrium, then each of its joints is also in equilibrium. Consider, for example, the two members that are used to support this known loading. If this member is in tension, then the forces at each of its ends must pull on the member, as you see here. If this member is in compression, then the forces at each of its ends must push on the member. Now let me draw the free body diagram of the joint at B. It looks like this, doesn't it? We have action, reaction, a pulling force on the joint, creating tension in the member, a pushing force on the joint, creating compression in the member, and of course, the known load. I can find these two unknown forces if I consider force equilibrium of the joint. In other words, I can apply these two equations to solve for these two unknowns. And essentially, that's what we use the method of joints to do. We write joint equilibrium for all the joints of a truss, and then we apply the two equations to each joint, and we find the forces in the members. What we've done here, essentially, is we've taken internal loadings in the members, and we've exposed them as external to a free body diagram, and then we've applied the two equations of equilibrium to determine these forces. And I'll show you how this is done numerically in the next lesson. But for now, let's consider just drawing a few free body diagrams of different joints to see more about what the method of joints is about. Let's consider this truss, which is in equilibrium with these external forces. And let's begin by drawing the free body diagram of joint D. There, of course, we'll have three forces acting. They look like this. We have the known force of 15 kilonewtons. We have the unknown force in member DC. And of course, we don't know the force in member DA. Now here, the force is pulling on the joint, so therefore the member, DC, will be subjected to tension, as you can see here. This force, of course, is F of DC, and so is this one. Now let's look at joint C. There we have three forces acting. Of course, action, reaction. Realizing that this is in tension, this has to be a tensile force pulling on the joint. And we'll have member AC pushing on the joint, so we'll have compression in it. I'll show that in a minute. And of course, we have another pulling force in CB. Let me label these forces. Here we have F of DC. This force, F of AC, and of course, F of BC. And to complete a free body diagram, we have to show the slope right in here. 3, 4, and of course 5. That's a complete free body diagram. Now we'll consider joint B down here. Actually, we have this intermediate member between the two joints. Here we have tension because it's pulling on the joint. Action-reaction pulls on the member as we would expect. This, of course, is equilibrium. This force is equal and opposite to this one, F of BC. And so down here we have pulling. And of course, we said this is F of BC. We also have the 15 kilonewton force acting. And we have the force of 20 kilonewtons. And finally, we have the force F of AB. A complete free body diagram. Finally, we'll look at joint A. But before we do, let's discuss what's happening to each member. For example, take member AB. Is it subjected to tension or compression? Well, we considered pulling on the pin here, didn't we? Therefore, the member will be subjected to tension. How about member AC? Is it subjected to tension or compression? Well, here we assume pushing on the pin, and therefore it'll be subjected to compression. And finally, look at member AD. Is it subjected to tension or compression? It's being pulled on here, isn't it? And so we have tension in the member. With all this in mind, now we can draw joint A. And there we have the following forces. Tension force, a compression force from here, of course, a tension force from here, and finally, our force of 20 kilonewtons. And to complete our free body diagram, we have to show the slope of the force here. And that, of course, is on a 4, 3, 5. To complete everything, though, of course, we have to label the forces. And we have F of AB, and we have F of AC, and finally, F of DA. These are complete free body diagrams of every joint of the truss. And as I stated earlier, we apply the equations of force equilibrium to each joint, and then we can figure out all the forces. Now, before we end the lesson, let's re-review the same problem we just finished, except now we won't draw the members, and see if we can just draw the joints, understanding what tension and compression really is. We'll begin in joint D. How many forces act there? Well, we'd have to put 3 on our free body diagram, wouldn't we? Here's our 15 kilonewton force, and here we have forces pulling on the pin. So are these members in tension or compression? They're in tension, aren't they? Let's go to joint C. How many forces on its free body diagram? There'll be 3. And here, of course, since we've stated this to be in tension, it must be in tension over here as well. It pulls on the pin. What about member AC? Is it in compression or tension according to the way this arrow's going? It'll be in compression, won't it? Because the force is pushing on the pin. And finally, what about member CB? Tension or compression? It's in tension. It pulls on the pin. Now we'll go to joint B. How many forces act on its free body diagram? There'll be 4. We have this force going up, pulls on the pin because it pulls on the pin here. And here we have the force of 15 kilonewtons, here's the force of 20 kilonewtons, and finally, the force of member AB on the pin. We're assuming it to be in tension, it's pulling on the pin. And finally, we have joint A. How does the force in member AD act on this pin? Does it pull or push? It has to pull, doesn't it? Because after all, we assumed it pulled up here, so we have tension in this member. What about the force in AC? Does it pull or push on the pin? It pushes, because it pushes over here. We have compression in this member. What about the force in AB? It has to pull, doesn't it? Because it pulls over here. And finally, we have our 20 kilonewton force that acts on the pin. Now do keep these ideas in mind when you go to the next lesson. But for now, we'll end this one.